Okay, I will talk about Gaussian channel capacity. The aim of this note is to show differential entropy for continuous random variables. So we've been talking about entropy for discrete random variables only, but we will extend that framework to differential entropy, which is for continuous random variables. So instead of summation, we have to use integration. That's the only difference. And second item is I will talk about Gaussian channel capacity and Gaussian coding theorem. So we can approach the capacity of Gaussian channel using Gaussian codebook. So that's the big difference. And the third item is we will talk about multiple Gaussian channels and water filling solutions. Okay, these three items are the left subject until the end of this semester. So with these three subjects, I will conclude the course materials for this semester. Okay, the first one, differential entropy. So most well-used continuous random variables include the uniform distribution and Gaussian random variables. So uniform random variables and Gaussian random variables are useful for us to describe things. But we don't have the entropy defined for these continuous random variables. So we will have to do it now. So that is called differential entropy. And we use a small letter h instead of a capital H that we have been using so far in order to show that this is a differential entropy. So differential entropy is defined this way. Instead of instead of px that we've been using, we will use the density fx. So instead of probability mass function, we will use probability density function, f of x. So hx, where x is the random variable, is defined to be minus integration over the support set of the random variable fx times log fx dx. So this is obviously has the similar flavor, right? So we had this one so far. But this has now this form in terms of integration. Okay, so that's the definition of differential entropy. And let's take a look at example. Uniform distribution over the interval from 0 to a. So a is a positive number. Then by applying the definition, we have this. So support set is from 0 to a. Density function is 1 over a, and the log over 1 over a, and we do the integration. Since log 1 over a is a constant, we can bring it outside. Okay, then we have log 1 over a minus log of 1 over a, which is the answer, and basically that is 1 of log a. Okay, so log a is the entropy of this uniform distributed random variable x, and log a can be negative when a is less than or equal to 1. Okay, so basically in this particular case, even though the interval, which is the size of the message set in the case of discrete random variable, so that's the I mean, this interval takes the role of the message set. So this interval has a length which is positive. That is obvious with the choice of value a, where a is a positive number. So we have a we cannot have a we cannot have negative interval length, right? The length has to be positive. So a has to be a is the length of this interval is positive, but log a, when we take the entropy, it can be negative. Okay, so that's what I have right here. So but 2 to the power of hx, which is a, is the volume of the support set. In this particular case, this is one-dimensional, so it is length. Length is the volume, basically. If you have a two-dimensional random variable, then can be area, and if it is three-dimensional, it is going to be volume. Okay, beyond the three-dimensional random variables, we can just say they are n-dimensional volume. So A denotes A means the volume of the supporter set, which cannot be negative, right? But when we take the log of that volume, it can be negative. So that's one thing that we have to be careful. Entropy may be negative in the case of continuous random variable. And so the differential entropy can be negative. Okay, so for a Gaussian random variable, the range is from the negative infinity to the positive infinity. The distribution has a bell shape, we already know, which can be described by its mean and variance. So in general, n by 1 Gaussian column vector x has the following distribution. Okay, so this is the probability density function for Gaussian column vector x. So this is n by 1. So we can talk about covariance matrix of x, which is n by n covariance matrix K, and mean vector n by 1 mean vector M. And then using K and M, we can describe the Gaussian probability density function. Okay, so this is well known. I hope you have seen this in random variable course. Okay, Gaussian random variables are used extensively to design noises and signals And we will show that it has the maximum entropy with a power constraint. Power constraint here means with the same covariance matrix, any distribution with the same covariance matrix, Gaussian has the maximum entropy. And we can also talk about fading channels when we study wireless communications. The channel coefficient is modeled as a Gaussian random variable. And sensing matrix in compressed sensing literature, we have Gaussian sensing matrix where the element of sensing matrix is Gaussian distributed. And then we can also talk about Brownian motion. Basically, Brownian motion is integration of Gaussian random variables, and then can be used to describe particle movement inside a box, or it can be described to talk about stock market volatility, things like that. So Gaussian random variables are very, very useful, and it is meaningful for us to talk about entropy of Gaussian random variable. And in order to satisfy the aim of this lecture note, which is to show Gaussian channel capacity and Gaussian channel coding theorem, in that regard, we need to study Gaussian random variables. Okay, so let's talk about entropy on Gaussian distribution. Okay, so here I have X, which is one-dimensional Gaussian random variable with a mean 0, variance sigma square. So that is nothing but fx, which is 1 over square root of 2 pi sigma square, and the exponential function whose exponent is minus half x squared divided by sigma square. And we can calculate the entropy in knots first, and then you can do the entropy in bits as well. So all you have to do is to use log base 2 in this definition. So that's all you had to do, and it will turn out that the answer came out the same. So expression came out the same. So in terms of doing it not first, where you have to use natural log right here in this position, and just by substituting this fx into into the argument of the natural log, we have this. So where do we have this? Because we have this, right? So since we have taken the log, natural log, all you had is the exponent. And on this one, we have to take the log, where this is where you have. And this first part is the only part that matters with integration, multiplication with fx. Since this is constant, you can bring it outside of the integration. Okay, so that's we have done. So on the first part, we are doing the integration. Okay, and when we do that, minus, so we have a plus, and we can bring out the constant term, which is 0.5, 0.5 over sigma square, and by definition, this is the sigma square. This integration right here is a sigma square, so all we have left is 0.5. and then log square root of 2 pi sigma square. Okay, when we put them together, we have half log 2 pi sigma square e. And when we do this again with log base 2, log base 2, basically we have to just change this with the log 2, okay? And we just need to follow this line right here, and then we will come up with the same result. But in this case, this has to be in bits because we have started with log base 2. Okay, log base 2. So this has to be in bits now. Okay, so that's the results so far. So entropy on Gaussian distribution have these forms. Okay, have these forms. These forms. And when we do that with the Gaussian vector, x is a vector now, and y one vector, then in the place of sigma square, we just need to replace it with the determinant of the covariance matrix, which is written this as the with the absolute value sign and k, where k is the covariance matrix of the Gaussian random vector. So this is the most general result. So you can take a look at theorem 8.4.1 of Carbo and Thomas to see the derivation, but the derivation is exactly the same as this one. Okay, but except that it is done in the for the case of n by 1 random vector x.